Hello, this is Ignacio Vigars, and I am going to present my probabilistic risk analysis of a passive safety system. More specifically, I am going to address the design of the passive core cooling system, also known as PXS, of the AP1000 nuclear reactor. In the field of reactor safety design, there are two types of safety systems: active and passive. In the active systems, there's a need for intervention from the personnel to handle and resolve the accidents and emergency situations. Active systems usually comprise a number of subsystems, equipment, or modules for successful application. Examples of these subsystems or components are diesel generators, power networks, batteries, pumps, monitoring systems, and other components that are labeled safety grade by the supervisory safety statutes. On the other hand, a passive safety system is one where both activation and performance rely on natural forces and phenomena. Examples of these natural forces are gravity, condensation, heat convection, and chemical reactions to regulate the temperature. In the generations 3 and 4, passive systems are gaining ground compared to their active counterparts. And this has several advantages. For example, in the event of emergency situations and accidents, passive systems allow the personnel to prioritize their own safety without compromising the entire nuclear facility or the environment. Under less drastic scenarios, the personnel is given time to gather the details of the incident, assess the options available, and procure resources as needed so as to resolve the problem, its root cause, and ramifications. Passive systems also lead to independency from external infrastructure and notably reduce the factors of common cause failures. A real-life example of common cause failure was the tsunami in Fukushima, as it impaired the power networks and flooded the basement where batteries were located and presumably the spent fuel was stored. Additionally, passive systems provide some degree of immunization from underlying deficiencies in training or from incomplete documentation on the operation of equipment under circumstances of emergency. Fukushima here is another example. When the tsunami hit the Daiichi nuclear power station, the personnel was not knowledgeable on how to operate the controls to release the heat, and to compound the issue, the manuals for those controls did not cover how to operate the equipment under similar conditions of emergency. One primary purpose of passive safety systems is to overcome the reactor coolant leakage, as well as to remedy some of the adverse developments arising from loss of coolant accidents. Another design feature that is gaining traction with passive safety systems is the reduction in the number of components. That simplifies not only the maintenance but also the safety assessment process, as it decreases the design complexity. The AP1000 is a pressurized water reactor that is built as an improvement over the design of AP600. In fact, the AP1000 almost doubles the capacity for power output, and its plant designed life without replacement of the reactor vessel is about 60 years. With regards to the safety, its predicted core damage frequency is about 40 times lower than the benchmark in the requirements, whereas the predicted frequency of significant release of radiation is 50 times lower than the benchmark in the regulations. Additionally, the AP1000 is designed so that there's no operator action required for 72 hours after the accident, and one may say that much of this is due to the prevalence of passive safety systems in this type of nuclear reactor. Here's a simplified diagram of the AP1000 PXS. From left to right, we see the in-containment refueling water storage tank, the core makeup tank, and the accumulator. The in-containment refueling water storage tank is combined with the heat exchanger. The purpose of these three components is to store water or evaporated water that will be delivered to the reactor in the event that the sump does not provide an adequate amount of coolant. The sump is not visible in this diagram, but if to a more complete version, we see the sump with its own system of check valves and control valves. In this more complete diagram, we also see a pressurizer and the automated depressurizing system. For purposes of this analysis, these two components are omitted. Note how the sump and the in-containment refueling water storage tank share a set of valves. This is relevant for when we construct the reliability block diagram. This RBD is a representation of a hybrid of the two previous diagrams. As we can see, the initial point is the sump with its own set of check valves and control valves. It's connected in parallel to the in-containment refueling water storage tank, and this is the reason why it was noticed that these two components share a set of valves. At the same time, the accumulator and the core makeup tank are connected as in parallel together with the sump, and they lead to the core. To close the loop, the core is conceptually connected to the heat exchanger and the in-containment refueling water storage tank. In the fault-free analysis, the undesirable event is the core melt. In the more complete version of the diagram, we see some components with an indication of representing multiple elements of similar type. When we look at the fault-free analysis, it becomes evident why it is helpful to consolidate similar items. In other cases, we will have a much wider tree, and that will complicate our conceptual understanding and analysis. Here, the undesirable event is the core melt, which will be the result of a simultaneous failure of the accumulator, the core makeup tank, the sump, the in-containment refueling water storage tank, and the failure in the system of valves shared by the sump and the water storage tank. To finalize this presentation, it is expected that borated water will be excluded from some nuclear reactors of generation 4. That includes also some designs like the pressurized water reactor. The reason why some of the components have borated water or boric acid is to lower the temperature and to procure a state of subcriticality, facilitating the conditions for shutdown. Two major drawbacks of using boron are its corrosive effect on several components and its impact on the nuclear fuel, leading to a shorter reactor life. Current efforts in research aim at decreasing or eliminating the usage of boron in cooling systems by replacing it with burnable poisons that control the neutron population without shortening the core life. Thanks for your time.